Hey guys, this is our fifth lecture about um, the energy, different forms of energy, and um, first law and energy conservation. Conservation, yes. So I hope that you've been enjoying this course. Please again let me know if you have any concerning core question. We can keep in touch through emails. Um, Before I start to solve this example today, I would like to go over the Blackboard because I've made some changes recently. So let's go to content and about the videos, lectures that I upload here in the lecture videos. You can see that there's like this embedded mm, like picture of this video that for any of these lectures. If you click on hit on play, it starts to play automatically, and then you can maximize it
Hey
with
guys,
these icons,
thank you for.
or you can directly click on the link. It takes you to the Panopto um, website. Then again, you can do
Hey
the same
guys,
thing. You can go and then maximize and watch the video. So therefore, we're not gonna use the Google Drive anymore. I'm gonna just directly upload the videos on the Panopto and then provide the links here for you. And also, so the lecture notes for chapter 2 have been posted 3, 4, and 5. I suppose that you took a look at them because we have this update on our lecture schedule. So lecture 3, 4, and 5 are your reading assignment, and then these related chapters for sections of chapter 2. The assignment number 2 will be posted, will be available at 8 a.m. So after 24 hours, you can see the solution as well. Well, so for today, here are the two examples that I want to go through. So in this lecture, I'm going to solve the first question, and in the following separate lecture, I will solve the second one for you. So let's solve it. Now I need to go to my, oh, I forgot to bring it up. Sorry about it. To my notebook. So example, let's say here is energy. Example 1. So please, as I told you before, please keep the question in front of you on your screen here because I will refer to the text, numbers, and information. So I assume you have it in front of you. Before I start, please take a look at lecture note number 3, pages 1, 2, and 4. Awesome. Okay. The question says that windmills slow the air and cause it to fill a larger channel as it passes through the blades. Okay, so we're gonna talk about a windmill, and as we see on the figure, the shape is uh, like some sort of like a diffuser. So we have two different type of uh, like these channels. We have a diffuser, and on the other side we have nozzle. So in the nozzle, the gas accelerates as it passes through the nozzle. The gas accelerates. So this is why we use the nozzles at the outlet of the airplane engines, because after the combustion, the gas accelerates and then it shoots out of the air, and so it helps the airplane to accelerate according to the third law, the Newton's third law. So, but here we are dealing with a diffuser that the velocity drops and decreases. So in the diffusers have this shape of expanding channel, and in diffusers the velocity decreases, so the air goes to the right and cross sectional area increases. Great. Let me continue reading the question for you. Consider a circular windmill with a 7-meter diameter rotor in a 8 meters per second wind on a way when the atmospheric pressure is 100 kilopascal, on the day when the atmospheric pressure is 100 kilopascal and the temperature is 20 degrees C. The wind speed behind the windmill is measured at 6.5 meters per second. Determine the diameter of the wind channel downstream from the rotor. This is the first part of the question. And then the power produced by this windmill, presuming that the air is incompressible. So the question asks for some sort of geometric parameter, which is diameter at the outlet, right? So whenever you're asked about geometry of your system or geometry of your design, you might need to take advantage of conservation of mass or conservation of volumetric flow rate, because as mass goes through your system, it can balance the geometry. It's like some sort of a link. The volume that goes through your system or the mass that goes through your system connects the inlet and outlet. So you can use this concept, which is conservation of mass, to solve for the geometry of your design. So, I mean, so let me make it in. I don't like this arrow. So let me tell you in mathematics what I mean. So, according to conservation of mass, here here's my inlet and here is the outlet, right? The mass coming in equals the mass going out, because there's no leakage from these boundaries of the diffuser or the windmill. Okay, so whatever that is coming into my system leaves the system. Conservation of mass, because it's in a steady flow. Therefore, the rate of the mass coming in equals the rate of the mass going out. And m dot is mass flow rate. Okay. Mass flow rate is defined as m dot equals density times v dot. That v dot is volumetric flow rate, and rho is density. Okay. Next step is we assume that the gas is incompressible. So density is constant. Therefore, rho coming in equals rho going out. So the density remains constant through your system as it goes through your system. Therefore, if I continue my equation about mass conservation, I have, this is what I wrote before, m dot in m dot out. Therefore, rho v dot in equals rho v dot out. Assuming that the gas is incompressible, these rows are equal, so I can cancel them. So for an incompressible gas, the volumetric flow rate is constant. For an incompressible gas. Okay. Now let me define the volumetric flow rate for you. Equals A times V. That V is velocity and A is cross sectional area. So the velocity of the gas times the cross-sectional area in front of it gives us the volume of the volume of the mass, the volume of the matter that is passing through our system. Therefore, A times V at the inlet equals A times V at the outlet. This is what we're gonna use. And please, please, please keep in mind that this equation was calculated assuming that density remains constant in the system. So if density is constant, if the gas is incompressible, it's not possible to compress the gas or compress the fluid, the liquid, then we can assume that density remains constant so that we can cancel out density from both sides and then end up with AV in equals AV out. Now, let's go and solve. Now we can use this equation and then solve our question. But, as I told you before, we have 2 steps to take before we start solving our question. The first one is, what is our system? Again, open or close, control volume or control mass. And another step was that we need to specify what we are looking for and what's the question. The question asks for the diameter at the outlet, one question, and the other one is the power. Please be careful to pay attention to this part. Power produced by this windmill. So the question itself is helping us, is showing us that we are supposed to find the power produced by who? The windmill. So it's telling us that peak windmill as your system. That's it. If you just pay attention to the text, then you can easily find what the system should be peaked, and then you can determine either it's a control mass or control volume. In this case, we are talking about a flow, steady flow passing through a windmill, passing through the diffuser. So we are focused, we are interested in a region, in a domain. Like imagine that you hold your hands around your eyes, and you just like a camera lens, and you're just looking at somewhere, and then people are passing by, or like there's a wind or cars or whatever. So this is the flow, but you don't move your head. You are just looking like straight in front of you, right? This is called control volume because the volume is the same and the mass is going through the system. But if you keep track of your friend on the street, then you are locked on your friend, and you are like monitoring him as he is walking. So you are like turning your head, and you are locked on a molecule, on a piece of mass. That would be a control mass. In this case, we don't care. The air is coming in and then going out. We do not track the air. We are just zoomed and focused on a portion, on a spot, on a specific position. So our system is control. It's control volume. And then let me draw the system for you. So we have real boundaries, the case of the diffuser, the case of the windmill, and we have inlet and outlet. So these boundaries are, but these boundaries are imaginary. This is real because it's like metal or whatever, but the inlet is open and exposed to atmosphere, and outlet as well. But so I mean, like, these dashed lines are imaginary boundaries. Okay, please pay attention to the way that you pick your boundaries. And you have this flow to the right. So we know that mass is coming in. Let me write it in parameters. We have m dot in and m dot out, right? And we are looking for d out, so we can use the equation that we proved here. AV in equals AV out, and then solve for the cross-sectional area at the outlet, and therefore we can find the diameter at the outlet. So I will start with this equation, AV the text it says that the windmill is circular. Therefore, cross-sectional area is pi over 4 d square. We can substitute the cross-sectional area in the equation. Therefore, v is velocity. Velocity outlet. Cancel, cancel. So I'm looking for d out, right? So d out square equals d in square times velocity at the inlet divided by velocity at the outlet. You can take the square root. So if you go back to the text in the question, it says that with a 7-meter diameter rotor, so here is 7 meter, 8 meter per second wind. So the speed is, let me write this information for you in red or blue. Speed of the air is 8 meter per second. On a day when the atmospheric pressure is 100 kPa, so here at the inlet I have 100 kPa pressure and 20 degrees C temperature at the inlet. The wind speed behind the windmill is measured at 6 point behind the windmill. If you look at the figure to the right, it means. So that is 6.5 meter per second. And then it asks for the diameter. So if you plug in all these information in that equation that they solved for at the very end, the out would be 7 meter times this is the diameter at the outlet. So we found we solved for the first question. Now I ask you please to take a look at for the second half, which is the power produced by this windmill. Please take a look at lecture number 3, pages 8 and 9. You can pause, go there, check it out, and then come back. Thanks. Well, so according to that lecture note, we know that Okay, we are looking for the power produced by the windmill. So when we talk about power, it means the rate of energy in time. So it asks for power, power, power produced by the windmill. Okay. So when we talk about power, it means rate of we're talking about rate of energy in time, not the energy itself. It's called E dot, right? And we should use this equation, E dot mechanical, for any flowing fluid. We have M dot equals, sorry, E dot equals M dot times the mass flow rate times P divided by density plus V squared divided by 2 plus GZ for any flowing fluid. Before we solve for the power produced by the windmill, we need to talk about the first law. Please check lecture note number 5, page 6. Awesome. Well, on this page, again, we're talking about rate of energy. Okay, according to this equation, we have E dot in minus E dot out equals dE divided by dt. Everything is in kilowatt. So what does this mean? Sorry. Again, we are talking about rate of energy in time, right? So assuming, let's say we have this system control volume, right, with imaginary boundaries, dashed lines, and I have the rate of E dot coming in and this rate of E dot going out of my system. So the balance or the difference between the rate of energy coming in and the rate of energy going out indicates that how much of energy will be remained inside my system as like leftover, right? Something is coming in and something is going out. Whatever that's missing left inside my system, and it helps um, the internal energy or the kinetic energy of my system to increase, right? So um, if there is no balance between this energy inlet and outlet, if there's no energy balance between these inlet and outlet energies, so it means that in time, as time goes on, um, the E, which is the internal energy, is the mechanical, like I mean the total sensible energy of my system, it changes in time, right? If there is no balance between the inlet and outlet, the energy of my system, which is the leftover of the system, which is this like the capacity of my system, it changes in time because there was not a balance in between. In the other word, let's make it the other, turn it around. If the process is steady, in time, then dE over dt equals 0. It's steady, doesn't change anything, right? So for in this question, for the windmill, sorry, um, first law says that E dot in minus E dot out. Sorry, I need to show these terms on my system here. So again, let me go back before I wrote them there. So the first law, it says that there's conservation of energy, right? Energy doesn't create itself or doesn't disappear. Whatever coming in should go out unless something is remained in my system and it increases the internal energy of the system. So here we have this m dot in, and as well we have this e dot in and e dot out. But also this windmill is producing energy, so energy can go out through these boundaries, real boundaries. Energy, call it energy sub power. So again, if I go back to my first law equation, then E dot in is coming in, so minus E dot out going out, and also there's another output, which is E dot power. That should be dE over dt. That, as we know, this system is steady in time, therefore that should be 0. Okay, good. Therefore, we can just take the e to the power to the right side and then rephrase our equation in this form, and I can substitute this equation e dot in equals m dot times whatever here to solve for, to connect everything to like velocity or altitude or pressure. These are the sensible parameters that I can work with, right? So I need to bring them inside my calculations. So m dot at this time we need to have some assumptions that pressure is constant all the way through the windmill because it works like a fan. So in the fan, if you like put your hands in the front of in front and at the back of the fan, you won't sense any uh, significant pressure difference. So pressure is constant. And also, there's no change in the altitude. They're all, if you take a look at my system here, this is my system. Inlet and outlet, they are all both at the same level, height. Now we can apply these assumptions in our equation, and also let me recall that mass is conserved, so m dot in equals m dot out. Therefore, so power. If we go back there, pressures are same at inlet and outlet. Gz and Gz are the same, so we will end up with just V squares at the inlet and outlet times the mass flow rate. Let's go back to my definition about mass flow rate. Where is it? Where are you? Oh, here. So by assuming that the gas is incompressible, then and so we can relate m dot to v dot and then to a times v, cross-sectional area times the velocity. In this case, we have the cross-sectional area, the diameter, and the velocity at the inlet solved, but we do not have the density, right? So m dot equals density times v dot. And here I need m dot, see? I need m dot to plug it in there. So I need to pause for a second, find m dot, and then come back and plug it in there. I know that m dot equals, as I defined it for you before, p dot times v dot, right? Rho times v dot, sorry. And I know that the volumetric flow rate equals the cross-sectional area times the velocity, okay? And I prefer to have this at the inlet because I know that the diameter is 7. I can find the area there. And I know that the velocity is 8 meters per second, so I can just plug it in there. These numbers are straightforward. I prefer to have, you can pick it at outlet, but the velocity is like 7.77, so it's difficult to work with. But still, the problem is not solved because now I do not know what is the density. If you go back to the text, as I summarized it here, it's talking about the pressure and the temperature at the inlet, right? And assuming that the gas, the air, is an ideal gas, I assume you remember ideal gas equation. So I assume ideal gas, then I know that PV equals mRT. So M divided by V, mass divided by volume, which is density, equals, keep P here and then R and T, move it to the left side. P over R divided by T, temperature and then the gas constant. Okay, great. I have pressure, I have temperature at the inlet. Let's define these guys at the inlet. So I can find rho, and I know that the rho at the inlet equals rho at the outlet. It's constant all the way. Great, awesome. Everything is in shape. so rho in. Let's solve for rho in, or rho in general, right? Because density is constant. Equals, P was 100 kPa at the inlet. R is 287 kPa times meters cubed divided by kilogram Kelvin times temperature was 20 degrees C. In Kelvin it's 293, plus just add it to 273. Assume you know that. Equals 1.189 kilogram per meters cube. Awesome. I found the density. Put it back there in m dot and solve for mass flow rate. Mass flow rate was rho times volumetric flow rate equals 1.189 kilogram per meters cube. AV, right? AV at the inlet. A is pi over 4 d square, which was 7 meters. This is A. And V, velocity was 8 meter per second. Equals 366.1 kilogram per second. We are almost finished. I'm sorry this one was a long lecture. Sorry about it. Now let me show you this equation again. E dot power m dot times that velocities. So I'm gonna put everything in there. 366.1. Hurry up. Times 8. This is at the inlet. Inlet square minus outlet square. Square minus 6.5. It's given. Divide by 2. Right? Oh, so everything is in kilograms, second, and meters. So we need to do a tiny unit conversion. 1 kilojoule per kilogram equals 1,000 meters square per second square. If you don't know how to do this, let me know. I will tell you. I don't want to talk about it in this lecture. Just send me an email. E dot power equals 3.98 kilowatt. That's it. You can go over the solution again, all these steps, and then check out what I did. It was straightforward. You can keep it in your mind, and if you solve those examples, I mean the assignment and the solution, check it with the solution, everything will be easy. Thank you for watching this lecture. Bye.